Hey there, and welcome to the Building Block. This week we're reviewing a fundamental topic, the International System and English units. Today we'll be focusing on equations affected by the gravitational constant in the English engineering system. In the English engineering system, things are not consistent. As we discussed in the previous video, 1 pound force does not accelerate a 1 pound mass by 1 foot per second. To make this system more consistent, we need the gravitational constant for converting mass units to weight units. Let's take a closer look at some equations affected by this constant. The first one is force, as we previously explained, and also the specific weight equation. Fluid pressure is another equation where we need to be careful. It's defined as density, denoted as ρ, times the gravitational acceleration field and height, resulting in pound force per square foot. Other equations affected by GC include kinetic and potential energy, which we'll delve into in future videos. The shear stress relating viscosity and shear rate will also be discussed later. Remember, you only need to apply this constant when working within the English engineering system, specifically with pounds mass. Let's work through two examples. In the first, we'll determine the material of a 12 by 12 by 0.5 inch flat bar weighing 20.41 pounds mass. The options are copper, mild steel, aluminum, and gold. Pause the video and try calculating it yourself. Firstly, let's go over the equations and units for specific weight. The volume is calculated by multiplying the dimensions. 12 times 12 times 0.5 result in 72 cubic inches. I don't like to learn out of conversion factors, so I stick to the basics. I know that 1 foot is equal to 12 inches. So by multiplying 72 by this factor, which is 1 foot divided by 12 inches, I can convert my volume units quite easily. The result is the following equation, which is 0.0417 cubic feet. The density of an object can be calculated by dividing its mass by its volume. The density here is 489.45 pounds mass divided by cubic feet. We obtain the specific weight by multiplying this density by the gravitational acceleration field and dividing it by the gravitational constant. Remember that on Earth, the gravitational acceleration field is 32.2 pounds mass feet divided by square seconds, so the result should not change in magnitude. Only the pounds mass are converted into pounds force. Remember, if you got it right, you hit subscribe. Now, for the second example, imagine an eccentric billionaire setting up a colony on Mars, where the gravity field is 12.24 feet per second squared. They brought reserves of Diet Coke with an approximate density of 60.55 pounds mass per cubic foot. As an engineer, your task is to calculate the pressure at the bottom of the 10-foot tank, assuming the pressure at the top is 0. Compare the result with one of the following 4 options. Now it's the time to pause the video and give it a try. Let's break it down. You have Diet Coke in the tank, starting with 0 pressure at the top. Remember, fluid pressure can be calculated using this equation. We have all the necessary data to calculate it. The density is 60.55 pounds mass per cubic foot. The gravitational acceleration field is 12.24 feet per second squared, and the height of the fluid is 10 feet. Now, we divide all of this by the gravitational constant. Take a moment to cancel out the units. Pounds mass cancel out with pounds mass, feet with feet, seconds with seconds, and pound force goes on top. The power of this cubic foot is now 2. So the pressure is calculated to be 230.165 pounds force per square foot. We'll explore more of these types of problems in upcoming videos. If you enjoyed this content, please hit that subscribe button. Join our blog. We'll build in our future, one blog at a time.